Good afternoon, everyone. My name is Ben Hockman. I'm a PhD candidate at Stanford University in the Aeronautics and Astronautics Department, and I'm going to present a hopper, which was just mentioned, that we've been developing for exploring microgravity environments. This is a collaboration between Stanford, JPL, and Jeff Hoffman at MIT. So I won't belabor the point that we're all convinced of, and that small bodies are very interesting from a lot of different perspectives to explore, for human exploration, planetary defense, and keys to our origin. But more than just doing in situ exploration, we really want to extend that now and do targeted exploration, especially for bodies that are very heterogeneous. So the big question, though, which we haven't really been able to answer, is how do you actually move around and do mobility on the surface of small bodies? And so let's start by taking a look at where we've done mobility in the past. So the first example of this, I guess, would be the Apollo Lunar Rover, and it looks something like that. Then we started the era of Mars, and this is just one of the many rovers. You're very familiar with Curiosity. But these rovers both have similar architectures. They have wheels, and that's because they operate in a gravity regime that's very comparable to Earth, at least within similar order of magnitude. But now we have an interest in visiting bodies that look like that, and these are actually generous depictions because these would be sub-pixel level at real scale. But Phobos would be an example. And now when you get to bodies that size, you're talking about gravity levels that are 3 to 5 orders of magnitude lower than Earth. So the question is, how do you adapt the mobility approaches that we've used in the past for bodies that are extremely foreign? So some of the challenges in doing mobility in microgravity is, well, the microgravity itself. And the reason you can't use wheels is because wheeled systems rely on their self-weight to create traction. And so when you have a rover that weighs as much as a paperclip, you don't have that force. Remaining attached is something that was illustrated by a lot of missions, but most recently Philly, that bounced over 1 kilometer. And then, of course, there's very irregular shapes in gravity fields, which Steph just mentioned, can make it very complicated to understand where a projectile might travel. And then, of course, we don't really know what the regolith and dust environment might be. So it seems over the decades, people have proposed various mobility approaches, but the community seems to have converged on the idea of hopping. Now, hopping lends itself naturally to microgravity because you have a tendency to want to bounce anyway. So I won't go over all of the projects that have been developed in the past, but I'll highlight 2 that are currently on the Hayabusa 2 mission to asteroid Ryugu. The top left picture is Minerva. It's a 1 kilogram rover with some simple cameras. And on the top right is Mascot 2. And these both have internal mechanisms that allow them to hop sort of randomly. They call them relocation mechanisms. But as I said, missed the slide. So now that we have the notion of hopping, we want to extend that and say, how do we actually do targeted mobility? And if you look at a body like Phobos that has very spectrally diverse regions, this could be very useful for constraining global characteristics of the body. So the project I've been working on, we call it Hedgehog. Now, Hedgehog is exactly that. It's an extension to these hopping concepts. And the basic principle is it's a small cube that uses internal flywheels with mechanical brakes to controllably hop and tumble. Now, when I say controllably, I mean you can choose the direction and the speed that you hop. And I'll go into how that exactly works. So the basic components are 3 internal reaction wheels, which are very common in spacecraft, but we use them in sort of a unique way. And that is we use motors and mechanical brakes to abruptly transfer momentum with the structure. And my next slide will go into how that actually creates mobility. And then the corners of this cube have what we call spikes, which are essentially bumpers for protection for collisions with the environment, as well as just feet for gripping the surface. So some of the key features of a system like this is there's no external moving parts. It's completely sealed mechanically and thermally, which helps it helps from a dust contamination point of view. The symmetric design allows mobility in any configuration. In other words, you don't have to self-right yourself. Any side is equally suited to doing mobility as any other side. And from a scientific perspective, it's basically just a shell that's capable of mobility, but has a lot of internal volume for packaging subsystems and science instruments. So the mobility system lends itself well to all kinds of payloads. And obviously, it's a scalable concept. So these could be ranged from anywhere from like a 1 kilogram size all the way up to maybe tens of kilograms. So the basic principle, which is basically illustrated in this video, is we spin up the flywheels very slowly to build angular momentum, and then by applying a mechanical brake, that very abruptly transfers that momentum. And we've spent quite a bit of time modeling this from an analytical, numerical point of view. So I don't have time to go into any of the details, but we've done a lot of analysis to determine how controllable this type of rover is from various different angles. And basically, this has yielded what we call a suite of motion primitives. Now, motion primitives are just a set of motions that you can execute to do various things on the surface, the primary being hopping, and that is hopping in the right direction and at the right velocity. But we also can do much more local fine maneuvers, such as tumbling. This would be just flipping over on one side if you wanted to point science instruments, and then just spinning about a vertical axis to do pointing for cameras. So one of the problems that any microgravity system has to overcome is testing, and this is particularly difficult when you're on Earth, where gravity is orders of magnitude higher than microgravity. So we've kind of done testing in a broad category, but I'll go over some of the three basic categories in which we've tested these systems. And the simplest is just to over-design it, which cannot always be done, but we have built a few prototypes, such as this one you see in the video, that are capable of moving in a 1G environment. So this is just simple tumbling on a beach, so it's very limited in terms of scale. The microgravity would allow it to hop much further. Then you can take the gravity offload perspective, and that is trying to basically turn down gravity with some kind of contraption. So we've developed many test beds over the years, but this is sort of our state-of-the-art. It's an overhead gantry crane that essentially offloads the weight of the hopper so that it moves as if it were in microgravity. So this video just sort of shows you in real time how that motion looks. And so the gantry provides the translational tracking, and this white gimbal allows it to passively rotate in all three axes. So this can emulate gravity down to about 10 to the minus 3 Gs, which is comparable to Phobos gravity. And it just starts to give you a perspective for how slow motion can be in microgravity. And then finally, about a year ago, actually, we've tested a couple prototypes on reduced gravity flights. And reduced gravity flights are particularly nice because you don't have to attach the rover to anything to offload gravity. The chamber itself is in free fall and effectively reduced gravity. So we went and got 4 days worth of flights on the Vomit Comet. And I'll just show you a few highlights from that. We brought several surface materials to test different maneuvers on, because we really don't know what the comet the physical properties of comet and asteroid regolith is. So this material, for example, is a comet regolith simulant developed by the Extraterrestrial Simulants Lab at JPL. It's basically a crushable foamed concrete, pumicite. Then you can do interesting things in the Vomit Comet, such as offloading granular media itself, which behaves quite differently under microgravity influence. The particles aren't cohesive, so it splashes in this sort of fluid-like way. This is just demonstrate that we can hop in any configuration. So in this case, it's hopping over a single spike. So it's not just limited to 90-degree orientations. And this is an example of how you might do fine mobility to point science instruments, just flip from one side to the other. This is what we call a yaw maneuver. If you want to point a camera or just shift your orientation, you could do something like that. And this one's my favorite. We actually tested this on a whim because we had done all of what we planned on doing. So we buried Hedgehog down in the sand to simulate what it might be like if we were stuck. And so the question is, could you use some kind of high energy maneuver to unstick yourself? And so we did this very aggressive spinning maneuver, which has this fantastic spraying pattern in the sand, which actually is one of the most useful results. And it says that you can, escape if you get embedded in loose regolith, but you might also be able to leverage this kind of maneuver for testing physical properties, doing a maneuver like this and then looking at the surface to see how it responds. So aside from a mobility system, this has to be a spacecraft as well. So this is an example of a baseline architecture we've developed for an notional mission to Phobos. And now Phobos is a very interesting target, but it's important to note that this sort of architecture is completely adaptable depending on the science objectives and the target. But one of the biggest advantages for this type of system and its shape and size is that it's able to leverage a lot of subsystems that have already been developed or are currently being developed for interplanetary CubeSats, so things like the Sphinx avionics board from NESF and other various science instruments that have become smaller and smaller. So like I said, it's a totally scalable design, and we say it goes anywhere from a few kilograms to a few tens of kilograms. So so we've also studied the autonomy of this thing, going from these controlled maneuvers to actually targeted navigation. You can think of this like playing a game of golf. You want to get to a very specific spot, but there's going to be some uncertainty in how you bounce around on the asteroid getting there, as Steph pointed out in his talk. So this requires A, knowing where you are in the first place, which is not trivial in a small body, and then figuring out how to get there, which also does not always mean hop towards the goal. There could be hazards in the environment, strange gravity fields that make this non-trivial. And then I talked about a lot of execution, what moves can we use to actually get there. And then finally, just hanging on for the ride. Since this really is just a hopping platform, we don't have a propulsion system, so we do this iterative process of hops and coming to rest. I'll just touch briefly on the approach for localization. So you can find out generally where you are on the body using inertial and optical sensors. This can kind of constrain your position more regionally. Then you can use some techniques that are sort of a hot topic of research in robotics, using vision to more accurately refine your position relative to a global map. So I'll skip this video for now. And then the motion planning side. And motion planning takes an interesting flavor on small bodies. These videos, on the left you see a potential map, on the right you see effective slope. And of course 67P is a very irregular body, but this is not uncommon for small bodies like Itokawa or other interesting targets to have very inaccessible regions from a dynamic slope point of view. So that makes planning very interesting. So we use a lot of the work that Steph's been doing in terms of running dynamic simulations to essentially learn how we can move. This is just an example of a Monte Carlo simulation you could envision, where you throw a bunch of hoppers, accounting for all the different various sources of uncertainty, and you can see that you get these weird distributions. And so I think with that, I'll skip the ConOps is you would deploy one or many of these, you do a sequence of hops and tumbles to get to some targeted spots, and then essentially you repeat. And the mothership would be in the loop for helping with navigation. So in conclusion, robotic exploration has become a hot topic for NASA and space agencies around the world, but the mobility is very challenging. So this Hedgehog concept offers new science capabilities at an affordable cost. And that's key, at affordable cost. So we could potentially be a secondary payload on a number of missions. So ongoing work is refining the planning and control strategies, doing synergistic approaches with the mothership to do more robust localization and planning. And if I have time for questions, I'll take some questions.
We've got time for questions.
Derek, go ahead. Very interesting, thank you. How do you spin up the wheels, and what does that require? Have you got 3 motors in there that require powering and all the rest of it?
Yep, just simple brushless motors. And in fact, in microgravity, you want to spin them up very slowly as to not counter-rotate. So you want to essentially build momentum in a static position. So yeah, just very simple off-the-shelf motors would do the trick.
And they don't take up a large volume mass?
No, in fact, the motors themselves can be embedded in the flywheels, so the actual mobility system is
solar powered, or?
Excuse me?
How are they powered?
They're powered with a DC motor.
Just have a battery?
Yeah, battery. Yeah, primary batteries would be the...
That sounds like more math.
Yeah.
Ben, it seems like when you on spin-up mode, you could also expose some fresh material.
Absolutely.
In addition to just getting yourself unstuck.
Yeah, I think it'd be really interesting to do a study of how we can leverage this type of aggressive kicking to explore the physical properties, whether it be observing the accelerometer responses and gyros, or even just optically looking at the surface after you've uncovered these materials. Yeah.
Really quick. Yeah. Okay. I was wondering if you've used the motors or attempted to simulate using the motors for arresting your motion upon landing on one of these hops.
Yeah. So the problem of bouncing is not easy. because you don't never really know exactly how you're going to strike the surface, especially when it's really uneven. So we could, I mean, we have these flywheels, so we can do counter spin, for example, if we want to like maybe put some backspin on the rover before it hits the ground. We haven't really explored this in too much detail yet, but there could be a number of different damping approaches, so to speak, for reducing the coefficient of restitution on bouncing, and that might be pretty interesting.